Okay, let's unpack this because every single time you open an app on your phone or, every time you click a link on a website.
Or even just pull down to refresh a social media feed.
Yes, exactly. Pulling down to refresh. There is this invisible, honestly, incredibly complex negotiation happening right under your fingertips.
Yeah, it really is invisible to the user.
Right, you don't see it, but across the network, there are distant computer systems talking to each other.
And they're making demands, trading data, agreeing on rules in literal fractions of a second.
It's wild.
Yeah.
So today, our mission on this deep dive is to equip you, the listener, with a really powerful mental model.
Right, to decode those invisible conversations.
Exactly. We're looking at a fascinating stack of sources you sent us. We've got technical breakdowns, articles on API architecture, and your own notes on this concept called Greybox thinking.
Which is such a cool concept, by the way.
It really is. And the goal here is to explore how you can figure out exactly what these digital systems are doing,
Yeah.
even when you have absolutely no access to their underlying code.
Yeah, and I mean, it is such a vital skill for anyone working in or around technology today.
For sure,
And
because things get messy quickly.
Oh, absolutely. The moment systems have to communicate over a network boundary, the rules of the game completely change.
Mm.
You are no longer just running code on a single isolated machine sitting on your desk.
Right, it's not a closed loop anymore.
Exactly. That network boundary introduces, well, three very difficult, unavoidable challenges. You've got delay, failure, and ambiguity.
Delay, failure, ambiguity. So, like, a message might take too long.
Right, or it might get lost entirely in transit. Or, it might arrive totally garbled.
Huh. So if two separate systems, say, that app on your phone and some server sitting in a data center halfway across the world, if they're going to survive those challenges,
Yeah.
they desperately need a shared grammar.
They do. Without it, they literally can't function.
Right, because before that shared grammar existed, it was basically the Wild West out there.
Oh, completely. You'd have different engineering teams writing their own custom rules for every single connection.
Which sounds like digital chaos.
It was total chaos. So if you want to become a detective of these modern complex systems, we first have to learn the language they actually settled on to bring order to that chaos.
And that universal grammar of the web is something called REST, right?
Yeah, REST. It's an acronym that stands for Representational State Transfer.
Representational state transfer. Sounds very academic.
It does, yeah. But basically, it functions as an architectural style for APIs, and it is built entirely on top of HTTP.
And HTTP, or Hypertext Transfer Protocol, that's essentially the fundamental carrier pigeon of the web, right?
I love that. Yes, the carrier pigeon. It's the underlying protocol that dictates how messages are formatted and transmitted.
Okay, so why did we need REST specifically?
Well, to understand the core purpose of REST, you really have to look at the alternative. Because clients, like your web browser and servers, the machines actually holding the data, they're usually developed, deployed, and maintained completely separately.
By totally different teams, probably.
Exactly. Different teams, maybe different companies. So without REST, every single endpoint would become a custom negotiation.
Oh, wow. So every time a front-end system wanted to talk to a back-end system, the engineers would basically have to invent a new dictionary just for that one conversation.
Yeah.
Every single time.
That sounds like a total nightmare to maintain.
It was a massive headache. So REST exists to make distributed systems easier to understand by providing this highly predictable contract.
A predictable contract. Okay, I like that.
Yeah, with REST, the method you use, the URL you send it to, and the status code you get back, they already communicate a massive part of the system's intent before you even look at the data itself.
I really love the analogy for this that we found in the articles you shared with us, because it takes this super abstract software architecture and makes it very tangible.
The restaurant analogy.
Yes, the restaurant analogy. So think of an API, a REST API, specifically like a restaurant. When you walk in and sit down, you're handed a menu.
That menu is the API contract. It tells you exactly what you are allowed to request. You can't just order something that isn't on the menu and expect the kitchen to know what to do with it.
Exactly. They just look at you funny.
Right. So then you tell the waiter what you want, and they write down an order slip. That order slip, in this case, is your HTTP request.
Yep, the carrier pigeon.
The pigeon. So the waiter takes that slip, walks away, and pushes through those swinging doors into an invisible kitchen. And that kitchen is the back-end logic.
And you aren't allowed back there.
Exactly. You're stuck at the table. You don't know if they have 5 chefs or 1. You don't know how they're prepping the ingredients. But eventually, the waiter comes back through the doors and hands you a meal.
And that meal is the response.
Boom. It's such a perfect way to visualize it.
It really captures the dynamic brilliantly. You are interacting with a complex system where you don't control or even see the internal workflow.
But you still get exactly what you need because of that menu, that contract.
Right. And in the grammar of REST, that contract relies heavily on specific verbs to tell the kitchen what to do.
Okay, let's talk about these verbs. Because the system is organized around resources, right?
Yeah, things like users or video files or shopping cart orders. Those resources are located via URLs.
But to tell the system what you want to actually do with those resources, you use standard HTTP methods, which are the verbs of our shared grammar.
Exactly. So let's play this out with the restaurant analogy, because these verbs are really the foundation for the detective work we're going to do later.
Okay, so if I'm just looking at the dessert menu, deciding what I want, I'm not changing anything in the kitchen, I just want to read the data. That's a GGT request, right?
That's right. GetTT is strictly for retrieving data without altering the state of the system at all.
Okay, but if I actually want to submit an entirely new order to the kitchen, like I am creating a brand new resource, what's that?
That's when you use POST. POST creates.
Post creates. Got it. But what if the waiter brings my meal and I look at it and say, actually, you know what? I changed my mind. I want to swap this entire plate of spaghetti out for a steak.
You're replacing the whole thing.
Yeah, I'm replacing the whole thing.
In that scenario, you would use PUT. The PUT method is designed to completely replace an existing resource with a new one.
I feel like real-life kitchens would hate that.
Oh, they definitely would.
But what if I just want to change one tiny thing? Like, I just want to swap my side of fries for a side salad. I don't want a whole new order. I just want to update a piece of it. Would that still be a PUT?
No, and that's a really important distinction. If you only want to modify a portion of the resource, you use PAT-TCH.
PAT-CH.
Yeah.
Okay, so PAT-CH tells the server to just apply partial modifications, leaving the rest of the order untouched.
Exactly. It's much more surgical.
That makes perfect sense. And then delete is obviously just canceling the order entirely, removing the resource.
Right, taking it off the board.
But there are a couple of other verbs in this grammar that seem a bit more cryptic in the notes we reviewed. Like, what about head?
Ah, yeah, head.
If I'm the customer at the restaurant, how am I using a head request?
Well, think of a head request as asking the waiter a question about a dish without actually ordering it to your table.
Oh, okay. Like what?
So in technical terms, it asks the server to retrieve the headers, the metadata, without sending the actual body of the data.
Okay, give me an example of when I'd use that.
Let's say you want to know if a massive 10-gigabyte video file exists on a server, and you want to know its exact file size. You don't want to actually download all 10 gigabytes just to check if it's there.
Right, that would take forever.
Exactly. So you send a head request, the server replies with the metadata, saving you massive amounts of time and bandwidth.
Oh, wow. That's incredibly efficient. It's like asking the waiter, is the soup of the day vegetarian?
Right.
Without making them bring you a bowl of it.
That's exactly it.
Okay, and the last verb mentioned in the sources is options. What does that do?
Options is a way for the client to ask the server about the rules of engagement. It essentially says, how are we allowed to communicate about this specific resource?
So it's like asking the waiter, right when you sit down, do you accept cash or just credit cards? Before you even try to order.
Yes, you're checking the allowed communication methods before committing to any action.
Wow. This whole REST system is surprisingly intuitive once you map it out like that.
Well, what's fascinating here is that because REST is organized so strictly around these resources and verbs, it creates a very reliable, very visible cause and effect relationship.
Yeah, it's very structured.
Because the contract is standard, an engineer can logically infer the expected behavior of a system long before they ever have to inspect the backend code.
Which just saves everybody a headache.
Exactly. It reduces integration mistakes because the vocabulary is universally understood. REST isn't just popular because it's some fashionable coding trend.
Right.
It is immensely valuable because its predictability aggressively reduces friction.
Okay, so REST provides this beautiful, predictable contract. It's the visible menu, the standard verbs, and the meal that eventually arrives at your table.
Right.
But here is the major pivot in our sources. What happens when the meal never arrives?
The inevitable failures.
Yeah. What happens when those swinging doors to the kitchen fly open, smoke is pouring out into the dining room, and the waiter just yells, something went wrong, but you aren't allowed inside to see what actually caught fire?
That is the big question.
If we are stuck in the dining room, how do we figure out what went wrong in the kitchen?
Well, that is the core challenge of modern software development. And to solve it, we really have to look at the three different paradigms for reasoning about a system.
The three boxes.
Yes, the boxes.
Hmm.
In engineering, we generally classify these as black box, white box, and gray box thinking. And these paradigms basically define how deeply you can reason about a system based on your level of visibility.
Okay, so let's start with black box. If I'm a black box thinker, I'm basically just staring at the swinging doors, right?
Pretty much, yeah.
I only have visibility into the inputs and the outputs. I send a request, I get a response, or in this case, an error.
Right. You see what happened.
Yeah, I see what happened, but because I can't look in the kitchen, I have absolutely no way to explain why it happened. The reasoning is just shallow. I just throw my hands up and say, the system is down.
Yes. Black box thinking treats the system as entirely opaque. It's just a sealed box.
Okay, and then on the total opposite end of that spectrum is white box thinking.
Exactly. This is where you have full, unobstructed internal visibility,
Like X-ray vision.
basically. You can inspect the actual code paths, you can look at the database queries, you can see the entire server architecture directly.
Wow.
Yeah, the reasoning here is incredibly deep, accurate, and complete because it's based on the literal line-by-line implementation of the system.
Okay, wait. Let me challenge that for a second.
Sure.
Because if white box gives you total accuracy, unless you just walk into the kitchen and see exactly which oven is on fire, why wouldn't we just demand white box visibility all the time?
It's a fair question.
Right. Isn't full access just objectively better? Like if I'm building an app and integrating a payment system, I want to see the code so I can fix it if it breaks.
Well, in a utopian scenario, full access would be wonderful, but the reality is that pure white box environments are exceedingly rare.
Really? Why is that?
Because most developers simply do not have full access or the legal right to inspect every system they interact with.
Oh, I see.
Think about front-end developers building a mobile app. They are constantly consuming APIs built by a completely different back-end team, maybe even in a different country.
Or a totally different company.
Exactly. Or think about integration engineers who rely on third-party tools. You can't just call up a massive multinational payment processor and say, hey, my checkout failed. Can you give me the source code to your back-end database so I can debug it?
Yeah, they will laugh and hang up on you.
Absolutely. They'd never allow that.
Okay, fair point. You are constantly forced to interact with systems that are legally or structurally locked to you.
Which is exactly why most professionals must learn to live in the third paradigm, the gray box.
The gray box.
Yeah, gray box thinking sits perfectly in the middle. You have limited visibility, just like the black box.
But you don't just give up.
Right. Instead of giving up, you use strong inference to reason about the system.
Inference, okay.
You use your knowledge of common architectural patterns to form disciplined explanations about what is happening inside without pretending to know every hidden detail.
Okay, let's ground this with a specific example from the notes, because this really clicked for me.
Yeah, let's do it.
Let's say you send a request to an API, and the waiter comes back and hands you a status code of 500 internal server error.
A classic.
Right. So if you are a pure black box thinker, your investigation literally stops there. You just say, well, the server failed. Guess I'll try again later.
Exactly. And the white box thinker, on the other hand, would bypass the waiter, log directly into the server shell, open up the stack trace logs, and pinpoint the exact line of Python or Java that triggered the crash.
But our gray box thinker doesn't stop at it's broken. And they also don't have access to the server logs.
Right.
So they have to start inferring based on the context to start testing theories like, was the payload I sent too large?
Or did a downstream database connection time out?
Did the business logic hit an edge case? And then they adjust their very next request to test those specific theories purely by observing the changes in the server's response.
That's gray box thinking in a nutshell.
Here's where it gets really interesting. Gray box thinking is basically a superpower.
It really is.
You're diagnosing a patient without being able to run an X-ray. So how exactly do we use those REST clues we talked about earlier, you know, the verbs, the headers, the status codes, to actually execute this gray box detective work?
Well, it all comes down to understanding how a request travels and reading a system's response as a physical trace of its hidden behavior.
Okay, walk me through that.
In any modern API, a request doesn't just hit a monolithic wall. It moves through a pipeline of invisible stages.
A pipeline.
Right. First, it hits a router, which basically checks the map.
Okay.
Then it goes through an authentication layer, which checks your ID. Then a validation layer checks the shape of your data.
Like making sure it's formatted right.
Exactly. And then it finally hits the core business logic, which probably talks to a database.
So it's hopping through all these hoops.
Yes. And because each of those stages enforces specific rules, the final response you get is not just a random error.
Oh, it's structural evidence.
Exactly. It is structural evidence of exactly how far your request made it before it died.
Okay, so we are mapping visible clues to their hidden internal meanings. Let's decode these signals. If I am looking at the method and the URL of my request, what does that tell me about the kitchen?
The method and the URL help you reason about routing and resource identity.
The routing.
Right. The router is the very front desk of the system. If a request fails there, you know the server couldn't even figure out what path or resource you were trying to talk to.
Got it. And next you look at the headers.
Headers carry the metadata. They act like a VIP pass clipped to your request. So they help you reason about the authentication layer or how the server is handling caching.
And what about the body of the request? Like, if I'm sending a JSON payload, which, for you listening, is basically just the structured text file containing the data I want to send to the server.
Right.
What does the shape of that data tell me?
The shape of your JSON body helps you reason about the validation layer. The system has expectations, right? If the server rejects the body, you know it's acting protectively.
It's saying, I don't like the look of this.
Exactly.
Yeah.
It's evaluating the contents and saying, this data does not meet my internal criteria, which tells you exactly where the breakdown occurred.
And finally, there is timing and latency.
Yes, timing is huge. If a request suddenly takes 3 seconds instead of 3 milliseconds, even if it succeeds, a Greybox thinker infers hidden upstream dependencies.
Ah, so maybe the server had to wake up a sleeping database.
Yes.
Or maybe it had to run a really heavy calculation before it could answer.
Exactly. You are inferring internal architecture simply with a stopwatch.
That is so cool. Okay, let's apply this to some specific real-world failure scenarios from the text, because this is where the detective work really shines.
All right, hit me.
Let's say I send a request and I get back a 401 unauthorized status code. What is my Greybox deduction? How do I know what happened inside?
Well, a 401 unauthorized acts like a bouncer at a club. It tells you exactly where the failure happened in that internal pipeline we discussed.
Okay, so where is it?
It means your request failed before the business logic ever even reached the data layer.
Oh, so you don't need to waste time wondering if the main database is down or if the server ran out of memory.
Not at all. You know with absolute certainty that your credentials or your security token failed the very first checkpoint.
Man, that saves so much debugging time. Okay, what about a 400 bad request?
Oh, that's a good one.
Let me set the scene. The API was working perfectly yesterday, but today I updated my app, I added a brand new field to my JSON payload, maybe new user preference, and suddenly the server spits back a 400 bad request.
Okay, I see where this is going.
As a developer, I've spent hours hunting down missing commas in JSON. But what is the system actually doing here?
In that scenario, the system is performing a schema validation. The code on the back end is literally looking at the structural shape of your data.
And it spots the new field.
Right. It sees that new field you added, realizes it have absolutely no idea what to do with it based on its programmed rules, and bounces it back immediately.
Ah.
It is effectively telling you, look, I understand who you are. The router knows what resource you want, but the actual data you handed me violates my structural expectations.
So the Greybox thinker immediately knows to look at the differences in their payload, not the server's general health.
Exactly.
Okay, let's do another one. What about a 404 not found? I feel like everyone listening has seen a 404 error page while browsing the web.
Sure. Yeah.
But in an API context, how is the Greybox thinker deducing the mechanics behind it?
Well, with the 404, the detective work gets a bit more nuanced.
How so?
Because the Greybox thinker has to distinguish between two completely different hidden realities. The first reality is a missing route.
A missing route. Meaning
The URL itself is misspelled or just doesn't exist. Your request hit the router looked at its map and said, I have absolutely no idea where this path leads, and threw a 404.
Okay, so that's a failure at the very front door. What's the second reality?
The second reality is a missing resource.
Okay.
In this case, the URL path is perfectly spelled. The router recognizes it, passes it to the internal logic, and the logic queries the database for the specific ID you asked for, let's say user profile 99.
But user 99 isn't there.
Right. The database replies, user 99 was deleted yesterday. The server then passes that failure back up the chain and returns a 404.
Interesting. So it could be a typo in the URL or the actual thing in the database is gone. How do you know which is which?
Well, by tweaking the URL slightly, maybe requesting a user ID, exists and testing the response, you can infer whether you have a routing problem or a database data problem.
All without seeing the code.
Yeah, all without seeing the code.
I love that. And, it isn't always just about errors and failures, right?
No, definitely not.
Because what if I get a 200 OK, which is the standard HTTP response for total success, but the data I get back is stale?
Oh, this happens all the time.
Right. For example, I just uploaded a new profile picture. Server gives me a 200 OK saying, got it. But when I refresh my profile, it still shows the old picture.
Yeah, that is a classic, highly common Greybox scenario involving a concept called eventual consistency.
Eventual consistency.
Right. A black box thinker experiences that, gets completely confused, and assumes the system is just fundamentally broken.
Right. They think it said OK, but it didn't work.
Exactly. A white box thinker might log into the infrastructure and check the caching layers directly, but the gray box thinker infers the architecture.
They deduce what's happening behind the scenes.
Yeah, they realize, this is a globally distributed system. When I uploaded the picture, it saved to the primary database, which returned the 200 OK.
But it hasn't updated everywhere yet.
Precisely. But the system is still copying that image to all the cache servers around the world to make it load faster.
Oh.
So they deduce that the system relies on eventual consistency, meaning it will sync up eventually, but there is a slight delay.
That makes total sense. So where is all of this actually happening in the real world? Like, what is the daily ecosystem for these contracts and this detective work?
It is happening across almost every boundary in the modern digital landscape.
Wow.
Everywhere.
Truly. It's happening in browser to back-end communication every time a web application loads dynamic data.
Right.
It's happening when your mobile apps authenticate with remote servers to sync your messages. It's happening internally, too.
Like within a single company?
Yeah, when microservices, which are the dozens of smaller, separate programs that make up a single company's backend, when they need to exchange data securely with each other. They're using REST and Greybox thinking on themselves.
Exactly. And it is heavily relied upon for external integrations, like your shopping cart calling a payment gateway, or an app connecting to a third-party email provider.
So what does this all mean for you listening right now?
Well, it's a game changer.
It is. Because whether you are a QA engineer trying to intentionally break a system to find hidden bugs, or a front-end developer consuming an API you didn't write.
Or, honestly, just a curious mind trying to understand the massive technological landscape we all live in.
Yeah, grasping these patterns is what elevates you. It takes you from relying on pure passive observation, just staring at the swinging doors of the kitchen, to practicing disciplined system thinking.
And it allows you to navigate the unknown, the gray zone, with actual confidence.
It truly does. The overarching lesson is that you do not need to control or own the entire stack to deeply understand the stack.
Well said.
So, to quickly recap the journey we've been on today, REST and its vocabulary of HTTP verbs gives distributed systems a predictable communication contract.
Right. It's the visible menu that tells you what is structurally possible.
And Greybox thinking gives us a highly practical way to reason about those systems without needing full access to the internal code.
It's the deductive detective work that lets you understand what is happening inside the kitchen.
And exactly where a process failed without ever opening the door.
Exactly.
Together they make working with APIs and really the chaos of distributed systems in general explainable and manageable.
This raises an important question, though.
Oh, what's that?
And it's something I'd love for you to think about after we wrap up.
Okay, lay it on us.
We've spent this entire time talking about software, right? About APIs and HTTP requests.
Yeah.
But if Greybox thinking allows us to deduce the hidden internal rules of a software system purely by systematically observing its inputs, its outputs, and its response times,
Yeah.
what other complex black box systems in our daily lives could you start to decode?
Oh, wow. I see where you're going with this.
Think about social media algorithms. You certainly don't have the source code for why your feed shows you certain videos.
Definitely not.
But by observing what happens when you input a like or a share and timing the response of what type of content appears next, you are effectively Greybox testing that algorithm.
You're deducing the rules.
Exactly. Or think about massive bureaucratic institutions or even complex organizational structures at your own job.
Yeah, that's a great point.
How much of their hidden internal logic, their true priorities, could you start to decode by applying this exact same framework of systematically observing the contract and analyzing the response?
That is such a fascinating way to look at the world. It turns almost everything into a system that can be parsed and understood, even if it's locked tight.
Just takes a little detective work.
It really does. Well,
Yeah.
thank you so much for joining us on this deep dive into the source material. We really hope you walk away seeing the invisible contracts all around you just a little bit clearer. Catch you next time.